implications and go as far as we can in this presentation within this next 3 days. Okay, so let's start. Now, this is where we really start this course. The phases of fluid mechanics. How many of you have heard about Archimedes? Yes, tell us something about Archimedes. Yes, what do you know about Archimedes? What is the Archimedes principle? Okay. A mass displaces an amount of fluid equal to its volume, right? How about Newton? What do we know about Newton? Okay, laws of motion and what? Yes, Nana? He invented calculus. What else? Okay, gravitation. Remember, F is equal to ma. Okay? Yeah.
Okay, so at the end of this crash course, we are going to be giving certificates, really. You will be given certificates for us. So please, put on your thinking cap. I trust you. So let's move on. Yes.
Okay. Newton-Raphson method, numerical analysis. Okay. Leibniz. We are getting into deep calculus. Okay. Bernoulli. We've taken fluids, right? We've heard of the Bernoulli equation. Euler, also in fluids. Okay. And so on and so forth. Okay. All these great men have impacted the subject of fluid mechanics. Okay? It is on their work that the subject of computational fluid mechanics has been developed based on the governing equations and the mathematical formulations that they came up with. Okay? So when you see all these men here, hopefully someday your picture would also be displayed as coming up with something that contributes to the subject of fluid mechanics. Okay? At the end of this first series of lecture on computational fluid dynamics, I want you to understand what is fluid dynamics, computational fluid dynamics. Why is it important? Okay? And where it can be applied. Okay? The what, why, and where. Okay? In fact, I have an assignment for you to go back and research online various areas of applications when you are after this first lecture. Okay? I want you to understand what we mean by modeling. Okay? And you said you've taken numerical methods. I want you to understand how numerical methods impact computational fluid dynamics. Okay? Have some familiarity with computational fluid dynamics codes. What we mean by the CFD process. And finally, an example of CFD process. Okay, so let's turn to the first bullet, that is the what, why, and where. So CFD, in essence, uses mathematical formulations. Okay? We use mathematical formulations for a physical problem, and we simulate it using numerical methods. What are the numerical methods? Discretizing methods, using numerical solvers, using numerical parameters, using grid generations, and so on. Okay? So CFD in general is the simulation of fluids engineering systems using numerical methods. Historically, we've used analytical fluid dynamics. That means that you have the governing equation for fluids, and you can obtain exact solutions, such as coming up with a simplified form of the Bernoulli equation that you can use to determine, for example, what? What can you use the Bernoulli equation to determine? Pressure drop in a pipeline, right? Okay? We can use the Bernoulli equation to even model the speed of the fluid at the exit, or calculate the speed of the fluid at any point along the pipe. Okay? We've done this analytically, but we can also do it using computational simulation. Okay? The other approach, of course, would be to do it experimentally. Okay? The other approach would be to do it experimentally. If we can do it historically by analytical fluids and experimental fluids, then why is there a need for CFD? Okay? Why is there a need for CFD? Anyone? Yes, please introduce yourself. Okay. That's an excellent answer. Okay? On the analytical solution side, it's not every problem that you can come up with a closed form analytical solution. Okay? Particularly if the problem has non-linearities in it. Okay? Solving the differential equations to come up with exact solutions is very complicated. On the experimental side, it can be cost prohibitive to build a big experimental system to basically characterize or solve a problem. However, if you can use computers to simulate it, that will save time and that will save you on the cost. So particularly, CFD has been made possible by the advent of the digital computing, okay, and advancing improvements in computer systems. So why we use CFD? We use CFD for analysis as well as design. And I would also add here, right now, also for education. Okay? Now, in your fluids class, did you undertake any experiments? Did you undertake any lab? In your fluids class, did you do any laboratory work? No? You did pressure drop across pipe. You did some experiments, right? Now, you can do all of that. So when I say education, we can use fluid mechanics, we can use computational fluid dynamics to teach you the pressure drop in a pipe. We can use computational fluid dynamics for you to visualize what we mean by when we say, oh, there is laminar flow in a pipe. Okay, or there is turbulent flow in a pipe. Okay, seeing is believing, right? So we can use CFD to visualize that. Okay, so it helps us analyze and it helps us design more cost-effective and more rapid than experimental fluid dynamics. CFD provides high-fidelity database for diagnosing flow field. Okay, 2, simulation of physical fluid phenomena that are difficult for experiments. Well, full-scale simulations. Imagine you have to design a new ship, okay, or design a new aircraft. And as part of the work as an engineer, you have to determine the lift forces, the drag forces, the aerodynamic forces on the ship, okay, on the ship submerged in the sea, in water. You still have to analyze the hydro forces on the ship. Okay, we can do those full-scale simulations using CFD. Body layer, stellar evolution, all of that can be modeled using CFD. Now, the other part of this is also using other computational simulation means that Dr. Boachi also alluded to when he mentioned density functional theory. Okay, that has more applications in the physics. So we use CFD knowledge and exploration to really understand the flow physics pertaining to various engineering applications, both in the analysis and design. So let us look at some specific examples of where CFD is used. Aerospace engineering. We look at this F-18 jet warplane, fighter aircraft, okay? The release of these missiles that are attached to it, okay? The impact forces, or even the wake around the aircraft as it impacts other fighters in its vicinity, all can be analyzed by CFD. Okay? In the design of the aircraft, not only are we looking at the aerodynamics around it and also looking at the lift forces, but we're also trying to mitigate or to come up with the control systems that impact various applications or that impact various problems that the plane may encounter. In the automotive industry, now you see all sorts of fancy cars that are now being designed. Okay? A long time ago, we just needed a transportation that moved. So they just designed a box system and put an engine to it, and it moves. Okay? It takes us from point A to point B. Now, in the racing industry, we've heard about Formula One racing, right? In Formula One racing, well, the aerodynamics of the automobile, of the race car becomes very important. Okay? And so we need to design the car such that we will reduce the drag forces on the car and make it go very fast. Okay? Not only do we use CFD for the external features of the car, even the combustion, okay, in the engine, in the internal combustion engine, the intake and the exhaust from the combustion pistons can all be analyzed using CFD. In biomedical applications, here you have temperature and natural convection currents in the eye following laser surgery. Now, to do cataract surgery, a long time ago in cataract surgery, they will have to cut the lens from your eye carefully to do that surgery, okay? Now they can do it with a laser, which is more precision. But then the question is, how does the heat input from the laser impact your eye, impact the blood vessels of your eye, okay? That can all be analyzed using CFD, okay? Or even the flow or transport of drugs within blood vessels, okay? That can all be analyzed using CFD. So CFD now has a wide application in biomedical applications. In chemical processing, okay, this is a schematic of a polymerization reactor vessel, and in it you can predict the flow and separation of the resident time effects within this system. Okay, in the process industry, when you have heat exchangers, okay, you can basically use CFD to characterize the heat exchange between various fluids during the process. In the design of buildings, when you want to look at the impact of these air conditioning systems, okay, you can use CFD to analyze the flow of the air conditioning in the room and see how it affects the temperature in the room so that we, the occupants, can be comfortable. Okay, in hydraulics, okay, such as this scored downstream of a flood control system. Just imagine that you have the Akosombo Dam, okay, and the floodgates are open such that downstream it basically flows uncontrolled. It would impact the environment, or it would impact the inhabitants downstream. How do we make sure that we carefully open these floodgates such that you don't cause havoc downstream? Okay, so again, we can use CFD to analyze open channel flows. Okay, in hydraulics, you can use CFD to analyze the flow of oil. We have petroleum engineers here, right? Okay, we can use CFD to analyze the flow of oil or the flow of gases within pipes. Let's move on to the next. Okay, so here in the marine, okay, so in the marine environment, you have this body basically in the marine environment, and you want to basically analyze the forces, the drag motion of the object submerged in the water. Okay, why is that important? Because the deeper you go, the higher the pressure forces that you have, right? And so you want to be able to characterize whether maybe am I using the right materials for this marine structure, such that as I go down deep into the water, it is not basically compressed and collapsed. Oil and gas industry, we look at this drill bit. Okay, we look at this drill bit. Can we characterize the flow of lubrication mud over the drill bit? Okay, we can use CFD to do that. In power generations, where you are also releasing a lot of, here from the cooling tower flows to the environment, how does the release impact the environment in the vicinity? You can use CFD to analyze that. This is an American football, okay? And we can use CFD to look at the aerodynamics in sports. This is football. It could be regular soccer ball. It could be golf balls, and so forth. Any comments or questions about the what, why of CFDs and how it's used? Yes?
For the sake of those of us from the atmospheric environment, if you could throw some light on CFD application in atmospheric science.
Okay, that's a very good point. And remember, you have a homework problem. I'm giving you some examples here. I want you to go back, research, and come up with additional examples as we learn, okay? So in the atmospheric realm, okay, when you want to do a lot of climate predictions, just imagine all the cars that you have in a given area. You know, because of the emissions from the car, you can have smog in your environment, okay? And so the question is, how does the concentration of these emissions impact the climate or the weather in the environment? Okay, we can use CFD to analyze that. So long as we do understand, okay, all that this boils down to is understanding what are the governing equations to apply to a given scenario. Okay, and what are your boundary conditions, as we'll see later on in applying to a given scenario. Okay, does the problem in doing the CFD analysis involves any chemical reaction or not? Okay, more questions or comments? More questions or comments? Prof, did I answer your question?
Yes, sir.
Okay.
I think even earlier in the previous slide or so, you mentioned emissions or
Right. Yeah. So here, you know, the environmental effects and the hazards. Okay. Pollution. Well, what causes pollution? Pollution can be caused by emissions from chemical plants, okay? Whether the chemical plant is producing, you know, releasing a lot of sulfur to the environment, okay? The environmental plant, the plant, or like I said, traffic, your vehicles is producing a lot of nitrogen oxide or carbon monoxide to the environment, and so on and so forth. All of that basically can be analyzed using CFD.